Let's continue. And so the strain energy, we will try to calculate the strain energy for one element first. And how do we describe the elements, the x and y? Okay. Remember for the map and the inverse map elements, the range of the x, y, and the range covered by this element will be defined by the inverse geometric mapping. So So the range of the entire mass element plus the inverse geometric mapping can tell you what are the x and y range for this element. So we will consider the c and the eta, both parameters. They should be changed from the -1. Okay, and what is the z values? Okay, if the T is the thickness of this element, then the Z values should be changed from negative T divided by 2 to positive T divided by 2. Okay, so we assume the Z equal to 0 is the neutral. Okay, the plate is located in the middle of the plate. Okay, so that's the range of the Z values. Since later we will try to use the numerical integration. So also we can define a third parameters. Okay, let's assume a zeta value changed from -1 to +1. Remember, if we use the Gaussian quadrature, the Gaussian quadrature can be used only for the range from -1 to +1. Okay, so if we define the zeta like this one, then you can, by a transformation formula, z is equal to zeta times t. So we can use the transformations. It is a linear transformation. Zeta times a constant t divided by 2 can give you the z value. Okay, then bring it to the screen. I will erase this one. Okay. Remember, the Jacobian represents the area ratio between the xy plane, the area in the xy plane divided by the area in the mass element. Okay, so the Jacobian times dc and the d eta will be the dx and the dy. And t divided by 2 times d zeta can give you the dz. So that's the calculation of the strain energy of the entire element. We need to change the integration over the entire volume to the integration of for the C beta and the zeta. So we need to do these transformations, and then you can move the elements which are not functions of the C eta, the zeta, to outside of the integration. So this one include okay, so the 1/2 U transpose will take in front of the integration. U vector will take out the integration also. Okay, so then the integration of this one can give you the K matrix. The integration of this one can give you the K matrix. Okay, so this one. And also remember, when you use the Gaussian quadrature, actually most of the time we will use the two-point rule. If you use the two-point rule to calculate this one, okay, so it means the C value we will take two integration points. Also for the eta values, we will change it for two different values. Also for the zeta values. So totally we have 8 integration points, and you need to calculate the integration functions for all these 8 points. The integration function include B transpose dB times T divided by 2 multiplied by the Jacobian. And for these integration functions calculated at the 8 integration points, then you need to multiply the corresponding weight. The weight will be the weight for the 3 directions. If we use the two-point rule, the weight for all points they are equal. So if you use the 8 point, then you need to calculate the integration functions for all 8 points. Then just sum up. Then you can get element stiffness matrix, K matrix. Okay, I think that's the most important part for the plate bending element. And let me remind you how can we get the D matrix. Okay, copy this one. Sigma, the matrix, sigma vector, the stress vector will be can be calculated by multiplying the D matrix by the strain vector. And we have 6 terms. And for the plate bending element, actually it is similar to the plane stress element, since the epsilon z close to 0. And the sigma z also can be neglected. So usually we just assume the okay. Usually the first 3x3 matrix, they are same as the plane space elements. And we have these two, D44 and the D55. And for the shear stress and the shear strain, for the YZ direction and the ZX direction, the two vertical shear strain for the plane element. For the since we need to integrate the when we calculate the strain energy, we need to integrate over almost all points inside the element. Since we need to cut the elements into infinitely small volume and calculate the typical point inside the volume to calculate the strain energy. So the shear strains, the shear strains, we need to consider they are located over the entire volume. Okay, so for the shear strains and the shear strains, since we have the free surface at the top surface and the bottom surface, so the tau yz and the tau zx, both the terms, they are equal to zeros at the top face and the bottom face. But usually we have the maximum. Usually we have the maximum shear stress and the shear strain at the middle of the plate. Okay, so at the middle of the plate, which is the usually we can get the maximum shear strain and shear stress. But you should know the shear strains and the shear stress. They are not constant throughout the thickness. So for different points along the thickness, you have different shear strains and the shear stress. But when we define the shape functions, remember this one is the top surface. That's the bottom surface. And that's the middle. That's the one. We can say that's the neutral plane. The shear strains and the shear stress, they are equal to zeros at the top and the bottom. And at the middle, we have the maximum shear strains and the shear stress. But when we describe the displacement functions, where do we define the displacement function W? Remember, we just described the displacement functions at the middle surface only. Okay. We assume the displacement functions. Actually, we assume the W for z equal to 0. But for different points along the vertical axis, we will say the W, they are same as the W in the middle. So if we describe the W only for the points on the middle, then when we calculate the partial W to partial X or partial Y to partial W, if the W functions, it is defined only for the points on the neutral plane. Then when we calculate these two partial derivatives, they are the rotations. They are the rotations of the horizontal axis about the horizontal axis, and also the theta x and the theta y. Okay, the theta x and the theta y, they are the rotations of the vertical axis. And the vertical axis, usually we also define the vertical axis. They are normal to the neutral plane. Okay, so the vertical axis actually it is located at the point on the neutral plane. Okay, so that's original. It is an axis vertical normal to the neutral plane. After the deformations, then we can measure the rotation of this vertical axis about the x-axis and about the y-axis. Okay. So remember the theta x and the theta y, they are the rotations for the vertical axis. And these vertical axis, they are defined for the points on the middle plane. Okay, so then if we combine the theta x and these two partial derivatives, then you can say okay, remember this sentence. The calculated gamma yz and the gamma zx, they are the shear strengths for the points on the neutral plane. Okay, but remember the shear strengths, they are not constant throughout this one. So these two, they are the shear strengths for this one. So if we multiply the shear strength directly by the shear strength, then you can say you did not consider the variation of the shear strength throughout the thickness. For different z value, these two terms, they are calculated for z equal to 0. But for different z values, actually the shear strength and the shear stress, they will be changed. So actually it is the similar to the when you use the form factor. It is a correction factor which can correct the Remember, what is the form factor? If we calculate for the frame elements, for the frame elements, first we need to integrate. That's the results we need to calculate. Sometimes we will change it to the if we use the V divided by A, the V divided by A, which is the tau average, and the tau average, which is if we divide the shear force by the entire area of this element, it is the tau average, and we know the tau maximum. Usually it is 1.5 tau average. Okay, so average, and for actually we have to calculate the exact integration for each different point. We like to use the sectional force divided by A to get a tau average, which is much easier to calculate. But in this case, we need a form factor to correct the calculated results to the exact solutions. For the exact solutions of the shear strains and the shear strains, it need to be. Okay, so we have a similar concept not only for the frame elements, also for the plate bending elements. When we calculate the strain energy due to the shear strains and the shear strains, we need a correction factor. And most of the time, we will put the correction factor in the D matrix. Okay, the two correction factors for the plate bending elements, and you can check the reference to find how can we use the exact integration to get the accurate results. Then we can create the correction factor. And right now, I just give you the results of this correction. And for these two vertical shear straits, we need to when we define the elements in the G matrix, we need to divide the G value by 1.2 for the D44. And also for the D55, we need to divide the original shear modulus for the material by 1.2. Remember, these two correction factors, they are obtained from the if we compare the results, the accurate results from accurate integration, and the shear strains calculated only for the point on the neutral plane. Okay, so these two, they are the correction factors. Okay, I think I will finish the lesson here, and I will give you the problems of the term project through the Moodle, and I can tell you that the problems, they will come from this lesson. So the problems for the term project come from the plate bending element. So please watch the videos carefully and prepare them carefully. And probably I will give you the problems for the term project on Friday. And I will give you, I will mention this again. The problems actually close to the homework. So it is not so difficult. It is just like homework problems. But I will ask you to turn in the term project in, I think I will give you 2 days. So you need to turn in the term project, let's say, before the end of the Monday. Okay. So the Monday night, 12 o'clock, before that time, you need to turn in your term project. I will give you the problems for the term project